All right, so here we are going to see a new specific category of differential equations that we're going to solve. But I think it's important for context that we just quickly recap the story so far. So chapter 4 is all about solving nth order differential equations. And what we've been looking at so far are nth order linear equations with constant coefficients. So that would be something like 3y triple prime minus 7y double prime plus 2y prime minus y equals, and then something on the right. So these are linear, and they have constant coefficients. And that's all we've dealt with so far, right? We know that when g of x, or the right-hand side here, is 0, we've been calling this homogeneous, and the method of solution is by working out the auxiliary equation and solving that. We'll get, some m values. In this case, we'd get 3 m values. Maybe some of them are equal to each other. And we know how to build the complementary solution out of that. Of course, if this were not 0, if it were a non-homogeneous equation, well, we put our attention on that in 4.4 and 4.6. And the method was actually to, for a moment, pretend it's homogeneous and find these m1, m2, m3, our complementary solution, and then either using the method of undetermined coefficients or variation of parameters, we would find a particular solution, and then we would adjoin that to the complementary solution, giving the general solution to the differential equation. Okay, yeah. So, unfortunately, the same relative ease with which we can solve higher order linear differential equations with constant coefficients does not carry over to linear differential equations with variable coefficients. There are a few exceptions to this, and the main exception we're going to work with are Cauchy-Euler equations. That's what we're dealing with today. So what is a Cauchy-Euler equation? Well, let's see. Okay, so it's just a linear differential equation of this particular form. So instead of the coefficients of the dependent variable being simply constants, now they're monomials, and they're specific monomials, the power of x matching the order of the derivative in that term. Okay, so again, this is probably a little more clear to accept with specific second or third order examples. So let's quickly look. So a second order example would look like this. ax squared y double prime plus bx y prime plus cy equals some function of x. A third order Cauchy-Euler equation would look like this. ax cubed y triple prime plus bx squared y double prime plus cx y prime plus d times y equals g of x. So again, this is very similar to the case with constant coefficients that we've been dealing with for pretty much the entire chapter 4. However, what's brought in are these x to some power in every term, where again that power matches the order of the derivative in that term. There is a really convenient way of solving these, and of course we're going to take a look at that. It's going to feel a lot like what we've been doing already. So in order to motivate a process, let's put our attention on the second order Cauchy-Euler equation and see if we can come up with a way of solving it. Okay, so to reduce the clutter even further, let's make it a homogeneous Cauchy-Euler equation. Okay, one thing we do have going for us is that if we can find a solution to the homogeneous Cauchy-Euler equation, that means that we can solve non-homogeneous ones just by using the method of variation of parameters. Because the method of variation of parameters, as we worked it out, it did not actually require the coefficients to be constant. So, let's put our attention here. If you recall, when we first started working out linear homogeneous equations with constant coefficients in section 4.3, we started with the trial solution of y equals e to the mx, and then that induced the auxiliary equation, and we were able to root out what the conditions were on m in order for e to the mx to be a solution to that differential equation. Well, we're going to do exactly the same thing here with a trial solution of x to the m. Okay, so let's take some derivatives and then plug that into our differential equation and heck, see what happens. So the first derivative is mx to the m minus 1, and the second derivative is m minus 1 x to the m minus 2. Okay, so therefore, inserting those into the dE, we're going to get ax squared times y double prime. So that's m minus 1 x to the m minus 2 plus bxy prime. That would be bx and then y prime, which is mx to the m minus 1 plus c times y. So that's c times x to the m, and this is all equal to 0. Okay, so something nice happens in each of these terms. In this first one, we're going to get m minus 1 x to the m, and here we get bm x to the m and cx to the m. So, look, there's an x to the m in every term, so we can factor x to the m out. Okay, so this guy right here is our auxiliary equation. Solving it will give us exactly the conditions on m for which x to the m will be a solution to this differential equation. So in that sense, that's how it very much feels like what we've been doing already in 4.3. Now, it's important to note that this is not the same auxiliary equation from the y equals e to the mx trial that we were doing earlier. In other words, this is not am squared plus bm plus c, right? Also, we'd really like to be able to just throw away this x to the m out here, but we can't just divide by x to the m, because if y equals x to the m is a solution, the function x to the m includes 0 in its domain. However, we're going to see that in these cases, the solutions to the Cauchy-Euler equations that we're going to work out are going to have an interval of definition of either negative infinity to 0 or 0 to infinity. So let's remember that for a little later, but we don't really need to worry about that for our auxiliary equation. Okay, so the next thing we're going to do is just solve for m. Now, we will have the same three cases when we solve for m that we had earlier. Either we get two real unique solutions, or we're going to get two real identical solutions, or we're going to get two complex conjugate solutions. And fortunately, the way that we handle those is going to feel a lot like the way we handled them earlier. But there are some differences. But let's just write down quickly the most simple case, which is that if m1 and m2 are real and distinct, then the general solution is going to be y equals c1 x to the m1 plus c2 x to the m2. So let's look at an example first where that's going to happen, and then we'll get into how to handle the other two cases. All right, so first let's recognize that this is indeed a Cauchy-Euler equation. And you can tell because it's got powers of x in front of each dependent variable, and the power of x coincides with the order of the derivative in that term. So yeah, we want to now solve the auxiliary equation from this, but rather than memorizing the form of the auxiliary equation that we obtained a moment ago, I think it's just a good idea to start with the trial solution and plug them in directly a few times until you really understand the process. Not to mention, the auxiliary equation gets more and more complex as we work with higher and higher order differential equations. So let's just put in our trial solution of y equal x to the m. All right, very good. So let's plug those things in this thing. So we're going to get x squared times y double prime, that's m minus 1x to the m minus 2, plus 3x times y prime, minus 3y, which is minus 3x to the m, and that's equal to 0. Okay, so we have x to the m times this, plus x to the m times this, minus x to the m times this. So we can factor x to the m out. And here's our auxiliary equation. Okay, so let's solve it. So that's this thing. So we can see that m squared minus m plus 3m is m squared plus 2m minus 3 equals 0. Okay, so we have distinct real solutions to this auxiliary equation. Those are the exact conditions on m, for which our trial solution is indeed the actual solution to this thing. And by superposition, we can simply write that the general solution, we would get simply y equals c1 x to the first m, so that would be, say, 1, plus c2 x to the other m, so that's negative 3. That's a perfectly acceptable way to leave it. Or you could write it as c1x plus c2 over x cubed, if you wish. All right, so yeah, that's not too bad. Of course, we do need to consider now what happens if we have two solutions, m1 and m2, that are equal to each other. And it's not just as simple as introducing a factor of x. In fact, you can probably guess that will really complicate things when we're already dealing with powers of x. So what do we do? Well, we're going to do what we did last time we faced that particular crisis. And like last time, we will solve the problem using reduction of order. Okay, so yeah, how do we handle an auxiliary equation with repeated roots? Well, let's assume that we're solving the following differential equation. And this would induce the auxiliary equation, which can be written as am squared plus b minus am plus c equals 0. All right, well, using the quadratic formula, the roots of this equation are negative of this quantity here, plus or minus the square root of that thing squared, minus 4 times a times c, all over 2 times a. And if we're assuming that both solutions are equal to each other, then this discriminant here is equal to 0. So that means that our m1 is equal to m2, and that's equal to simply negative of b minus a, which we could write as, of course, a minus b, all divided by 2a. And therefore, one fundamental solution, which we can call y1, would simply be x to the m1, which would be x to that thing. All right, so the question is, what is the other fundamental solution? Because it must be linearly independent from the first one. Okay, well, yeah, like I said earlier, we're going to use reduction of order. Now, in order to use reduction of order, we're going to need to get the original differential equation into standard form. So let's do that first. So here's the original. Ax squared y double prime plus bx y prime plus cy equals 0. So standard form means that the highest order derivative has a coefficient of 1. So we're going to have to divide everything by ax squared. So we're going to get, okay, and we can call this guy here our p of x, and we'll call that guy there our q of x. Notice, by the way, that this is one of the reasons why we have to impose the restriction on the interval of definition for our solutions to either be negative infinity to 0 or 0 to infinity, because right now we are excluding any solution whose domain includes x equals 0. Okay, so we're now ready to use the formula for reduction of order to find y2. So y2, of course, is y1 multiplied by the integral of this thing. And y1 is x to the m1. And p of x is b over ax. All right, so what do we have here? Well, we can factor the b over a out of the integral, and then the integral of 1 over x dx simply is ln of x. Incidentally, you could make this ln of negative x if you wanted. If you were insisting on an interval of definition to be negative infinity to 0, then you would, of course, be dealing with only negative x values, which you'd negate before taking the ln. So the fact that we're just going to call this guy ln of x means we are definitely dealing with the interval of definition of 0 to infinity. And that will be the implied assumption from this moment forward. Okay, well, e to the negative b over a ln x reduces itself to simply x to the negative b over a. And we can write this as x to the negative b over a minus 2m1 dx. Okay, but what is negative b over a minus 2m1? Well, recall that m1 is a minus b over 2a. So this is equal to negative b over a minus 2 times a minus b over 2a. All right, so that's like negative b over a minus, of course, these little 2's cancel. So now we have a minus b over a. Okay, so common denominator, that's super cool. We have negative b minus a plus b all over a. Wow, this is just negative a over a. Wow, again, that's just negative 1. So this whole thing is negative 1, which is super awesome. This is x to the m1 times integral of x to the negative 1 dx. So this is x to the m1 times ln of x. That's what our y2 is. So when you have repeated solutions to the auxiliary equation in a Cauchy-Euler context, you're going to get that first solution, which is x to the m1, and the second solution, you just introduce a factor of ln x. And actually, you would just keep doing that, higher and higher powers of ln x, so ln of x quantity squared, ln of x quantity cubed, as needed to eliminate any duplications. All right, so hey, let's go look at an example. Okay, so here we have a Cauchy-Euler equation, and it's homogeneous. Good. So yeah, let's dig in. start with that trial solution. Again, if you know the form of the characteristic equation, which of course you'll start to recognize is am m minus 1 plus bm plus c equals 0, or alternatively am squared minus or plus b minus am plus c equals 0, sure, you can go straight to those, where a, b, and c are the numeric coefficients to these terms. But again, I recommend just practicing with the trial solution a few times, especially because for higher order differential equations, you're going to get a slightly different form of a characteristic equation. And so you might as well just understand where it all comes from. It's not hard. So I'm going to go into the trial solution, which is x to the m. So first derivative and second derivative. So we'll go put those things where they belong in the original differential equation, and we'll get our auxiliary equation. There's our auxiliary equation. Okay, so that's m squared minus 4m plus 4 equals 0. All right, well that factors to m minus 2 quantity squared. And we're going to get m1 equals 2 and m2 equals 2. So we, of course, have a situation, I'm sure this is no surprise, where we have repeated roots of the auxiliary equation. So no problem. The general solution in this case will be y equals c1 and then x to the m1, so x squared, plus c2 x to the other one, which is, of course, squared as well, but we can't have the duplication, so we need that factor of ln x. And if there were another one, say this were some third degree that gave us m1, m2, and m3 all the same, then we would go c3x squared and just introduce an ln of x quantity squared, and you would just keep doing that as needed, right? But of course that doesn't apply here. So we are done. Okay, so what about complex conjugate roots of the auxiliary equation? So first of all, let's assume we have the situation. So our first m would be, say, alpha plus I times beta, and our second one would be alpha minus I times beta, as, of course, solutions always occur in conjugate pairs. So it's not wrong to actually just go straight to our general solution and say, okay, well, therefore, the general solution would be y equals c1x to the m1, which would be that, plus c2 x to the m2, which would be that. So that's not incorrect, but it's grossly unfinished, right? So we would never actually do that, because we know that the complex numbers are very surprising in what they turn into, right? So this is actually going to turn into something trigonometric, and we want to represent that. So let's not do this, and instead, let's investigate this form here, x to the alpha plus I beta. Okay, well, let's note that this is equal to x to the alpha times x to the I beta. And we can also rewrite this factor here as e raised to the ln of x to the I beta. So this is equal to x to the alpha times e to the I beta ln x. All right, but beta ln x is just like our theta here, and we know that e to the I theta is cosine of theta plus I sine of theta. So that means that to continue this line of thinking, we can write this as x to the alpha times cosine of theta. Well, theta is beta ln x in this case. Beta ln x plus I sine beta ln x. Okay, now the beta ln x is inside the cosine. It's not cosine of beta times ln x. In fact, let me just really emphasize that by putting another set of parentheses here and here to be absolutely unambiguous. So yeah, taking advantage of the fact that we can form the general solution out of linear combinations and the flexibility of the constants, constant multiplied by constant is still just a constant, including I, which itself is just a constant, that means that we could write our general solution as y equal x to the alpha, constant c1 times cosine of beta ln x plus constant times sine of beta ln x. All right, now there was a little bit of algebra omitted here, but it was exactly the same algebra that we saw earlier when we were going through these steps in section 4.3, when solving homogeneous equations with constant coefficients. Okay, well, let's look at an example where there's probably a good chance we're going to need exactly this stuff. Okay, yeah, cool. Here's an example. So it's a Cauchy-Euler equation. Let's solve it. Okay, so plugging stuff in, we're going to get, let's just factor that x to the m out right now. We know that's going to happen. So we get our y double prime, which is m minus 1. We've already factored the x's, minus 3m plus 7. So there's our auxiliary equation, and let's keep solving it. All right, does this thing factor? Not easily. So let's go for Euler quadratic formula. All right, so we get 16 minus 28. That's negative 12. That's all over 2. So rad 12 reduces to 2 rad 3. And of course, because of the negative, this is going to be 2i times rad 3. And oh, that simplifies a little bit further to 2 plus or minus I rad 3. So here we have an alpha of 2 and a beta value of rad 3. Okay, super bueno. So we can jump straight to our general solution. So it's going to be x to the alpha, which is x squared, and then c1 times cosine of rad 3, that's our beta, ln x, plus c2 times sine of rad 3 ln x. Okay, so that's our general solution. And let's just stop and appreciate what we've accomplished. We started with this question. There's some unknown function that when you take its second derivative and multiply that by x squared, and you take its first derivative and multiply that by negative 3x, and take itself and multiply by 7, then you add those things together, you're going to get 0. What function are we thinking of? Well, not an easy riddle to answer off the top of your head, but we know math well enough to assert with confidence that the answer is this thing down here. I think that's pretty cool. All right, the final topic we need to address from this section is how do we handle a non-homogeneous Cauchy-Euler equation? And we have an example queued up right here. So yeah, this is a Cauchy-Euler equation, definitely not homogeneous. So what we're going to do is actually just solve it the way we might think, which is first we will solve the associated homogeneous version of this Cauchy-Euler equation. And once we have a y1 and a y2 out of that, we will find the particular solution using variation of parameters. Okay, now it's important to understand that undetermined coefficients is completely not going to work at all here, so don't even go there. We have to use variation of parameters to get that particular solution. So that's going to give us our YC, the complementary solution. Okay, so that's great. We just solve this guy with a big 0 over there. Cool. Okay, so let's get our auxiliary equation, which is going to be x to the m, and then we're going to have m minus 1 plus m minus 1 equals 0. Okay, so we're going to get solutions plus or minus 1, which are distinct real solutions. So that's kind of the vanilla case. That's awesome. So we know that our YC will be a constant times x to the first one, which is x to the 1, C2 times x to the other one. All right, so let's call this guy our Y1, and we'll call this guy our Y2. And now we need the particular solution, which we're going to use variation of parameters to find. Now, of course, variation parameters involves the right-hand side. And something needs to, because we haven't used it yet. But we need to be very, very careful, because the right-hand side in our use of variation of parameters, which we typically call f of x, is not x squared e to the 2x. We must get the differential equation into standard form before assigning our f of x. So that means divide everything by x squared in this case. Here's the original diffeq. And standard form will be y double prime plus 1 over x y prime minus 1 over x squared y is equal to e to the 2x. So this is our f of x here for the purposes of variation of parameters. So recall that u1 prime is defined to be negative y2 times f of x, all divided by the Wronskian. And u2 prime is positive y1 multiplied by f of x divided by the Wronskian. So we've got our f of x, we have our y1 and our y2, which are part of the complementary solution. So we just need to find the Wronskian. So the Wronskian is, of course, the determinant of this particular matrix. All right. So there it is. So our u1 prime is negative y2. Now y2 was x to the negative 1. F of x was the right-hand side of the differential equation in standard form, so that's e to the 2x. And this is all over the Wronskian, which is negative 2x to the negative 1. So our u1 prime is e to the 2x divided by 2. And we can integrate that right away. That means that our u1 is an antiderivative of e to the 2x over 2. So u1 is e to the 2x divided by another factor of 2, so we'll go over 4. So there's our u1, all right? Let's just find our u2, and then we're going to be done. So u2 prime is equal to y1 f of x over w. So y1 was simply x, and we have e to the 2x, which is our f of x, divided by the Wronskian, which is negative 2x to the negative 1. So our u2 prime is negative 1/2 x squared e to the 2x. That's not quite as clean as what we had a minute ago, but it's fine. We still know how to integrate that. We're just going to need to use integration by parts, which isn't at all annoying. So we'll let u be negative 1/2 x squared. Du will be that. All right, and UV minus VDU, so ultraviolet voodoo. Let's see what we have here. Okay, so what's our U2 equal to? We get U times V, which will be negative 1/4 x squared e to the 2x plus 1/2 x e to the 2x dx. Okay, so let's just work out this integral. And yay, integration by parts. All right, so what's our U2 here? It's negative 1/4 x squared e to the 2x plus the new round of ultraviolet voodoo. So U times V would be 1/4 x e to the 2x, and then minus the antiderivative of 1/4 e to the 2x dx. And this last integral we can easily integrate, so awesome. Okay, so we have our U1 and we have our U2, and so we're ready to put together our particular solution, which is U1 y1 plus U2 y2. Now this is not our general solution yet. This is just a particular solution. It won't even have any constants in it. So our U1 was e to the 2x over 4, and our y1 was x, and our U2 is all of this loveliness, and our y2 was x to the negative 1. I'm going to write it as 1 over x. So this is x e to the 2x over 4, and let's distribute that 1 over x into everything. So there's our particular solution. Aha, but look, these first two terms are not long for this world. So what we get is this particular solution, just 1/4 e to the 2x minus 1 over 8x e to the 2x. So now we can finally put together the general solution, which, as always, is the complementary solution plus particular solution. And therefore, our general solution is the complementary, which was C1x plus C2, let's write it as C2 over x, it was x to the minus 1, plus the particular solution, 1/4 e to the 2x minus 1 over 8x e to the 2x. And there it is. We should do a quick double check to make sure that none of the terms here are duplicated over here, because remember, we can just throw those away. And what I mean by that is if we had, for example, a plus 7x here, we could actually just combine that with the first term C1x, and so that plus 7x is completely superfluous, right? We don't have any such redundant terms here, so we are done.